Hello, and welcome to 12.6 and or problems, or I should say or and problems. Compound probability is probability problems that contain the word or the and, or the word or, one or the other. Probability of A or B. These are problems where the goal is to obtain a successful outcome for at least one of the given events. So the probability of A or B is the probability of A plus the probability of B minus the probability of A and B of both things occurring. This formula is sometimes called the addition formula. So a roll of a die. A single die is rolled, I should say not on time, but one time. Determine the probability of rolling a 2 or a 5. So the probability of rolling a 2 or a 5 is the probability of a 2 plus the probability of a 5 minus the probability of a 2 and a 5. Now the probability of a 2, that's 1 out of 6. Probability of a 5 is also 1 out of 6. Now it's not possible to get a 2 and a 5. You cannot roll a 2 and a 5 at the same time. So that's 0 out of 6. So it's 2/6, which is 1/3. How about the probability of an odd number or a number greater than 4? So probability of odd or greater than 4, that's going to be the probability of an odd plus the probability of a number greater than 4 minus the probability of an odd and a number greater than 4. So how many odds are there? There are 3 out of 6 odds. How many numbers are bigger than 4? 2 out of 6 numbers are bigger than 4. Then how many are odd and bigger than 4? Just one thing, that's 5. So 1 out of 6. 3 plus 2 is 5, minus 1 is 4 over 6, which is 2/3. How about a number greater than 4 or less than 2? Probability of greater than 4 or less than 2. That's a greater than symbol, less than symbol. That's going to be the probability of a number greater than 4 plus the probability of a number less than 2 minus the probability of a number greater than 4 and less than 2. Now the probability of a number greater than 4. There are 2 out of 6 numbers like that. Less than 2, there's just one thing, that's number 1. And there's no number that's going to be both bigger than 4 and less than 2. This is 3/6, which is 1/2. Okay. I'm going to need to scroll this up, so pause that if you'd like to pause there. How about a number greater than 3 or less than 5? That's the probability of a number greater than 3 plus the probability of a number less than 5 minus the probability of a number both greater than 3 and less than 5. Okay, there are 3 numbers bigger than 3 out of the 6. There's 4 numbers less than 5 out of 6, and there's 1 number bigger than 3 and less than 5. That's number 4. So 3 plus 4 is 7, minus 1 is 6 over 6, which is 1. So you're guaranteed to roll a die, when you roll a die, to get a number bigger than 3 or less than 5. Mutually exclusive, 2 events for which it is impossible for both events to occur simultaneously. If events are mutually exclusive, then the probability of A and B equals 0. So in that case, probability of A or B would just be the probability of A plus the probability of B. We saw this. We looked at a number being 2 or 5. They can't both occur. There's no place you could be 2 and 5. And when you're greater than 4 or less than 2, those are mutually exclusive events. Example 2, one card is selected at random. Determine the probability of selecting an ace or a 2. So probability of an ace or 2. Well, these are mutually exclusive. You can't be an ace and a 2. So that's just the probability of an ace plus the probability of a 2. That's 4 out of 52 plus 4 out of 52, which is 8 out of 52. That reduces to be 2 out of 13. A jack or a club. Now you can be a jack and a club. That's possible. So the probability of a jack or a club is going to be the probability of a jack plus the probability of a club minus the probability of a jack and a club. So the probability of a jack is going to be 4 out of 52. The probability of a club is going to be 13 out of 52. The probability of being a jack that's a club, that's one card. There's one jack that's a club, 1 out of 52. So 4 plus 13 is 17 minus 1 is 16 over 52. And that can be reduced to be 4 over 13. Feel free to pause that one. I'm going to scroll. Probability of A and B. These are problems which require obtaining a favorable outcome in each of the given categories, given areas. This is sometimes called the multiplication formula. When using the multiplication formula, always assume that event A has occurred when calculating event B, probability of B. So example 3, 2 cards are selected at random from this deck. We've got different colored birds with different numbers, different lions, or lions look all the same, frogs look the same, and monkeys look the same. Okay. Determine the probability of the following with replacement and without replacement. First, that they both show monkeys. So with replacement is A. The probability of monkey and monkey is going to be the probability of monkey times the probability of monkey, and that's 5 monkey cards out of 20 times 5 out of 20. That's 25 over 400. That'd be 1 over 16. Part B without replacement, so you're talking probability of monkey and monkey. It's probably the probability of monkey times the probability of monkey, which would be 5 over 20. So the first one was drawn as a monkey. The second one means there are only 4 monkeys left out of 19 cards left, because this is without replacement. 1 monkey card's taken out of the pot, so we have 4 monkey cards left over 19. That's 20 over 20 times 19, and the 20s cancel out. And leaves 1 over 19. Okay, what's the probability they both show 3 in the first case? Probability of 3 and 3. That's the probability of getting a 3 times the probability of getting a 3. Okay, so we have how many 3s? Looks like there are 4 3s. So 4 over 20 times 4 over 20. That'd be 16 over 400, which is 1 over 25. Probability of getting a 3 and a 3 in the next case. That means probability of getting a 3 for the first card times the probability of getting a 3 for the second card. 4 out of 20 for the first. Now if 1's gone, we have 3 cards left out of 20. Let's see, the 4 and the 20 can cancel. 4 over 20 times 3 over 20. Just to red so you can see that better. That's a 1 up here, and a 5 down there. Oh, that's 19. So we end up with 3 over 95. Okay, part 3 says the first shows a lion and the second shows a bird. So the probability of lion and bird is the probability of lion times the probability of bird. So there are 5 out of the 20 cards are lion, and then 5 out of 19 remain. Oh, this is with replacement. Out of 20 cards are birds. So we get, again, 25 over 400, which is 1/16. Probability of lion and bird without replacements is 5 over 20 times, okay, now we have 5 birds, but now 19 cards because the 1 card's gone, that first lion card's gone. This can be reduced 5 into 20. Use a 4 down below. So 5 over 4 times 19, I want to say 76. In the last case, the first shows a 2 and the second shows a 4. So probability of 2 and 4, probability of a 2 times the probability of a 4. Probability of a 2 would be 4 over 20. Probability of a 4 is 4 over 20 with replacement. That's 16 over 400, which is, again, 1 over 25. And the probability of 2 and 4. In the second case, it's probability of 2 times probability of 4. This time it's without replacement, so the 2 cards taken out of the pot. We had 4 out of 20 for that one. Now there are still 4 cards, but there are only 19 cards left in the pot. That's 16. I'm going to reduce first. That's 4 over 95. Okay. Okay, so feel free to pause that. I need to scroll up and continue here. Independent events. These are 2 events in which the occurrence of either event in no way affects the probability of the occurrence of the other event. Whereas dependent events, 2 events in which the occurrence of either event affects the probability of the occurrence of the other event. So when we drew with replacement, means you put the card back in, those are independent, but it's dependent when we pull out and keep it out. So without replacement, that's dependent. It affects the probability. So independent event, for an example of it, is drawing with replacement. Dependent, drawing without replacement. Okay, example 4. A couple has 3 children, assuming independence and the probability of a boy is 1/2. Determine that all 3 children are girls, all 3 children are boys, and the youngest child is a boy and the 2 other children are girls. This is an example of with replacement in each case. That's going to be 1/2 times 1/2 times 1/2, which is 1/8. The probability of 3 boys, it's going to be boy 1 and boy 2 and boy 3. Again, 1/2 times 1/2 times 1/2 is 1/8. How about the youngest child's a boy and the other 2 are girls, so that's the probability of girl 1 and girl 2 and boy for the third child. What's interesting here is you get the same thing. 1/2 for the first child being a girl, 1/2 for the second child being a girl, and 1/2 for the third child being a boy. That's 1/8. Okay. And feel free to pause. I'm going to scroll up so we can do example 5. A sample of 50 people yielded the following information about their health insurance. Okay, so we have a number of people, type of insurance, managed care like an HMO, traditional insurance like a PPO, and no insurance. So 2 people who provided information for the table were selected at random without replacement to determine the probability that neither had traditional insurance. So I'm going to say this is M for managed care, T for traditional, and N for no insurance. So we're looking at probability of no for the first one and no for the second one. That's going to be the probability of no, or N1, times the probability of N2. Probability of no for the first person is 7 out of 50, and for the second it would be 6 left out of 49. So the 7 and the 49 can cancel or reduce. The 6 and the 50, you could get a 3 there and get a 25 here. And we're looking at 3 over 175. How about the probability that both have a managed care plan? So that's the probability of managed for the first and managed for the second. Probability of M1 times probability of M2. It's 24 over 50 times 23 over 49. That's 552 over 2450, which is 276 over 1225, or approximately, or not even approximately, you can do exactly 0.225. In the third case, at least one had traditional insurance, so the probability of at least one had traditional, that's 1 minus the probability that none had traditional. So the probability of no traditional is going to be the probability of no traditional for the first one times the probability of no traditional for the second one. Okay, so if 19 are traditional, that means there are 31 non-traditional. And if the first one is gone now, that means there's one less non-traditional. That means 30 are left out of 49. That gives us 930 over 2450, which is 93 over 245. Make this a little bit smaller. Now, back to the previous one, 1 minus the probability of no traditional is 1 minus 93 over 245, and that is going to be 152 over 245. And the last one from this example, probably the first had traditional and the second had managed care. So this probability of T for the first and M for the second. That's probability of T1 times probability of M2. So probability of traditional for the first one is 19 out of 50. And then we have 24 HMO people out of 49 left because it's without replacement. This is 456 over 2450. It can be reduced to 228 over 1225. Okay. On to our last page then. So feel free to pause it if you need to write that down. Here we go. Which formula to use? This is from the book. I'm not sure those page numbers are correct though. In fact, no, I don't think these are even in the book anymore. So I'd probably cross that out. But it is sometimes difficult to determine, so get rid of that, when to use the OR formula and when to use the AND formula. The following information may be helpful in deciding which formula to use. The OR formula, OR problems, will almost always contain the word OR in the statement of the problem. For example, determine the probability of selecting a heart or a 6. OR problems in this book generally involve only one selection. For example, one card is selected or one die is rolled. Whereas AND problems often do not use the word AND in the statement of the problem. For example, determine the probability that both cards selected are red, or determine the probability that none of those selected is a banana, are both AND type problems. AND problems in this book will generally involve more than one selection. For example, the problem may read 2 cards are selected or 3 coins are flipped. And that's it for this section. So that's it for 12.6. So send me your questions. Thank you.